Alright, this is your 5.6 video. Our learning intention is, as it has been, to derive and integrate a variety of functions. So more specifically, your success criteria for lesson 5.6 is to derive the inverse trig functions. And so before we do that, we need to actually review a little bit of our knowledge about inverse trig functions from trigonometry. And so I have here the three graphs of inverse sine, inverse cosine, and inverse tangent. If you recall from inverse sine, this is just the inverted sine curve. The problem is it doesn't pass the vertical line test and is therefore not a function in this format. So to make it a function, in the history of mathematics, what they did was they just took it and cut it right here and right here. So that now the only part of the graph that exists is just this little S-curve right here, and you could draw a vertical line anywhere through those, and it would pass the vertical line test. So this part doesn't exist anymore, neither does this part down here. Whoops, I need to back up on that. All right, so erase this part to right there. So now the inverse sine curve is only this little bitty S curve right here, passes the vertical line test. So basically this is negative 90 and this is positive 90. So that's why we say anytime you're doing an inverse sine problem, you must give answers in the coffee cup handle, because as far as the function is concerned, it's restricted from negative 90 to positive 90. So this graph down here represents the unit circle. This one's just an x and y axis coordinate plane. But on the unit circle, your inverse sine answers are restricted from negative 90 to positive 90, or you could think negative pi over 2 over positive pi over 2, the coffee cup handle. And when you're doing an inverse cosine problem, here's the graph of inverse cosine. Same thing we ran into with the other one. It doesn't pass the vertical line test, so this one got restricted from here to here. So now this graph is restricted from 0 to 180 degrees. And so that's why an inverse cosine problem, you only give answers as far as the unit circle is concerned. You would give answers between 0 and pi, only quadrants 1 and 2. And then inverse tangent, this is what an inverse tangent graph looks like. And remember, when you invert the tangent curve, there would actually be a whole bunch of these curves. There would be more up here. But to restrict it so that we pass the vertical line test, we just use this one in the middle. And so you can see it also goes only from negative pi over 2 to positive pi over 2. So that's why on the unit circle, I have to restrict this graph to the coffee cup handle, just between negative pi over 2 and positive pi over 2. So let's do a few inverse trig problems just to refresh your memory. Remember, when you see the word arc, that notation means the same thing as this notation. Inverse cosine of negative 1/2. So this is an inverse cosine problem. So I would be restricted to only give answers in the rainbow. So positive inverse cosine here, negative inverse cosine here, because x is positive here and x is negative there. So since I have a negative value here, that means I'll be giving a quadrant 2 answer. So think about what angle measure, if I want to know my reference angle, what would my reference angle be in radian measure if my adjacent was 1 and my hypotenuse was 2? Think back to the 30, 60, 90. If my adjacent is 1 and my hypotenuse is 2, that means this is my reference angle, which is 60 degrees, or pi over 3. So I have a 60-degree reference angle in quadrant 2 in radians. Remember, 60 means a 3 on bottom, so this is 3 pi over 3. So if I want a 60-degree reference angle in this quadrant, then that would be 2 pi over 3. So the answer to this is simply 2 pi over 3. Only one answer. All right, so similar problem down here. We have arc cosecant. So arc cosecant would mean inverse cosecant of 2 radical 3 over 3. Well, when you think of your special triangles, cosecant would be hypotenuse over opposite. I don't have any hypotenuses of 2 radical 3 or any opposites of 3. So chances are this thing has been rationalized. So what would it have looked like before it got rationalized? And if you don't know, you could multiply the top and bottom by square root 3 as well. And if you did that, 2 radical 3 over 3, and you unrationalize a denominator the same way you rationalize it, so that'd be 2 square root 9, which is a 3, over 3 square root 3, with those canceling, so now I have 2 square root 3. So this is exactly the same thing as 2 over the square root of 3. So I'll erase that now. If you've had time to get it down, or you can just rewind if not. So 2 over the square root of 3. So I now have cosecant inverse of 2 over the square root of 3. And remember, a secant is simply a sign flipped over. So at this point, if you'd rather write it as a sign problem, it might make more sense to just flip it over and write it as a sign problem. Alright, so now I'm looking for an angle measure that has an opposite of radical 3 and a hypotenuse of 2. And remember, this is an inverse sign problem. Inverse sign problems have to be in the coffee cup handle. I can only give answers between negative pi over 2 and positive pi over 2. So since mine is a positive problem, sign is positive in this quadrant and negative in this quadrant, so I'm going to want to give a quadrant 1 answer. And so what has a opposite of radical 3? Once again, 60 degrees. So if I have a 60-degree reference angle in quadrant 1, that's simply pi over 3. All right, one more review problem. This problem here, I have a tangent of an arc cosine. So another way to write that would be tangent of inverse cosine of radical 2 over 2. Now once again, you don't have any adjacents that are radical 2. You have a hypotenuse that's at a radical 2, but not an adjacent. So probably this has been rationalized. If you recall, square root 2 over 2 is the same thing as 1 over the square root of 2. So maybe we think of this problem like this. And of course, if your opposite's 1, or your adjacent's 1, and your hypotenuse is radical 2, that means our reference angle is 45 degrees. So the answer to this would be 45 degrees, or in radian measure, pi over 4. So the answer to that is a pi over 4. But I still have a tangent in front of that pi over 4. So what's the tangent of pi over 4? That's the same thing as saying what's the tangent of 45 degrees. So the tangent of 45 degrees would be opposite over adjacent, which is 1 over 1, just 1. So there's the answer to my review problem, example 3. All right, now we're ready to move on to actually doing some derivatives of inverses. So if I want to find the derivative, let's first of all write it like this. And it doesn't matter if you prefer the arc tangent notation. You can definitely do that. I'm also going to make the square root x and x to the half. So that's what I have to find my derivative of. I'm looking for f prime of x for this function. So keep in mind, whatever this graph looks like, I'm looking for an equation that would calculate slopes of tangent lines. And so to do that, I need a derivative formula. So if you look at page 4 in your math Bible, I've got it right here, using some part of that page we haven't used before. So these are all the derivatives of inverse trig problems. And right here, I have the derivative for inverse tangent. The derivative of inverse tangent is 1 over 1 plus x squared. So if this is more complicated than just an x, which mine is, I'll have to use the chain rule. And whatever you have here that value will be squared right here because it says x is squared. So if I have a square root x, so down here I'm going to have the square root of x squared. And then, because this is more complicated than an x, I will have to multiply times the derivative of that as well. So 1 over 1 plus x squared. So this derivative, the derivative of inverse tangent, just writing down what was on the other page, was 1 over 1 plus x squared. So I apply that to this. My derivative is 1 over 1 plus x squared. But remember, I don't have an x. I have an x to the 1/2, and that is squared. And because that is more complicated than just an x, I have to multiply times the derivative of this. So multiply times the derivative of x to the 1/2. So if I do that, I'm going to have 1 over 1 plus, if you take a half, square root, and you square it, they cancel each other out and you're left with an x, because a half times 2 is 1. So I have 1 over 1 plus x, and that is times the derivative of this. The derivative of that would be 1/2 x to the negative 1/2 power, just using the power rule there. So to simplify that, I would probably write that like this. 1 over maybe 2 square root x times 1 plus x. Okay, and that would be an acceptable answer. This is already on the bottom. I'm shoving this down to the bottom, so that's what this is right here. This 2 is right here. This negative exponent I'm shoving to the denominator, and that's right here. And then I have this left. And so I could distribute that. I'm not sure what the answer in the back of the book will be, but if you were to distribute that, you might see it written as 2x to the 1/2 plus, let's see, that's an x to the 2, so that'd be 3/2, so 2x to the 3/2. So either one of those would be acceptable answers. All right, and that was your example 4. All right, example 5, we have h of x equaling 5 times cosine, and you can leave this notation like this if you would like, or you can change it to inverse sine notation like this, whichever way you prefer. All right, so now I need a formula for, well, first of all, keep in mind this is the object, this is the angle measure of my cosine. So if when I'm think about the derivative of 5 cosine theta. So this is like my theta. If I was to take the derivative of cosine, that would be negative sine. The derivative of any cosine is negative sine. I just have something more complicated than a theta, so that means I'll have to use a chain rule here. All right, so first of all, I am paying attention to this, and I'm pretending like that's just a big theta. So the derivative of that would be negative 5 sine, because the derivative of cosine is negative sine. And for now, I keep this the same, but because it's more complicated than just a theta, I have to multiply times the derivative of that. All right, so I have this portion of my answer, and now I have to multiply times the derivative of this, which I'll have to look up in my math Bible. For right now, we'll write this down. Times the derivative of that. So let's go look at the formula for an inverse sine. Inverse sine is right here. The derivative of inverse sine is 1 over the square root of 1 minus x squared. And remember, I don't have an x here, I have a 3x here. So that means I'll have a 3x parentheses squared right here. And because that's more complicated than just an x, I'll have to multiply times the derivative of 3x. One over 1 square root. Was it a minus or a plus? It was a minus. So that right there is the derivative of an inverse sine. So I have to take the derivative of this using this formula, but instead of an x, I have a 3x. So I'm going to have 1 over the square root of 1 minus 3x, quantity squared, times the derivative of this, which is 3. Alright, so now I need to simplify that. So I've got all of this as part of my answer. This is the derivative of this thing. I had to multiply times the derivative of this because it was more than just an x. And so let's see, what's that going to look like if I simplify it? Well, let's see, I could take this negative 5 and multiply it times this 3 to make a 15. So I would have a negative 15. And then I have sine of inverse sine of 3x all over the square root of 1 minus 3x squared. Alright, well, as long as x is a positive value, we can cancel out these two things right here. You have a sine and an inverse sine. They cancel each other out just like if you do times 2 and then divide by 2. You do plus 5 and subtract 5. If you do an inverse sine with a sine, they cancel each other out, and you're left with just a 3x. So I've got negative 15 times 3x because these cancel each other out. And so now, and that 3x times 3x is also a 9x squared. I could do that. So now I have negative 45x over the square root of 1 minus 9x squared. And that is our answer for example 5. That was kind of a tough one. Alright, example 6. Example 6 has two terms in it. The first term is going to require a product rule because you have two things multiplied together and they both have an x in them. This one's the derivative of an ln, which I have a formula for that, but I'm going to have to use a chain rule and multiply times the derivative of this. My 1/4 will just kind of stick along for the ride. Alright, so to start with, let's do our u and our v for the first term. I'll kind of put those down here at the bottom. We'll say u is x, and v is inverse tangent of 2x. So that means my u prime is 1, and my v prime, I used that one just a minute ago, but we'll go look it up again. Inverse tangent is 1 over 1 plus x squared. 1 over 1 plus x squared, but I don't have an x, I have a 2x, so that would be a 4x squared, and now I have to multiply times the derivative of this, which is just a 2, and I'm going to put that 2 right here instead of out here. Okay, and so there's my v prime. So now I'm ready to do the product rule for the first term. I have u prime v plus v prime u. So u prime v is simply going to be inverse tangent of 2x. Just took u prime times v. Now plus v prime times u. V prime times u is this times this. That's like an x over 1, so that would make a 2x on top. So 2x over 1 plus 4x squared. Alright, then I have a minus sign with a 1/4, and the derivative of a logarithm is always 1 over that value, and then because it's more complicated than an x, I multiply times the derivative of the inside here. So the derivative of this would be an 8x. So I'm multiplying times an 8x. Alright. Move this down out of the way. Alright, so let's simplify what we can. Looks like we have a inverse. I think I could cancel these. That'd make a 2. So I'm going to have inverse tangent of 2x. I'm going to put that over 1. Plus 2x over 1 plus 4x squared minus a 2x over 1 plus 4x squared. Well, look what's happening here. These two terms are exactly the same. I got this 2x because I have a 2 and an x over here because the 8 and the 4 cancel, but these two terms are exactly alike. They're going to cancel each other out. Anything minus itself is 0, so now my answer is just inverse tangent of 2x. And that will be your answer for example 6. All right, moving on to example 7. It says find the extrema. Remember, extrema are maxes and mins, local maxes and mins. And to find out where those are, those only happen at horizontal or vertical tangents. So I want to find the derivative of this, which represents the slope of a tangent line, and then figure out where that tangent line slope might be 0 or undefined. So f prime of x will equal, let's see, we have an arc sine. Let's go look at the formula for that again. We had it a second ago. It's 1 over the square root of 1 minus x squared. 1 over the square root of 1 minus x squared. That is the derivative of an arc sine. I have just an x, so I don't have to use the chain rule at all. And then for the second term, I have a 2x. The derivative of a 2x is simply a 2. All right, so I'm going to need to set that thing equal to 0 and also figure out where it's undefined. If I'm going to set it to equal 0, I'm probably going to want to find a common denominator here so that I have one fraction instead of 2. So my common denominator would simply be the square root of 1 minus x squared. So this fraction doesn't need changed at all, that numerator. This one I would have to multiply this times this, so I got to take the 2 times that. And now I would have something that looks like that. Okay, so what will make it 0, and will anything make it undefined? So what will make my numerator come out to be a 0, and what will make my denominator come out to be a 0? Well, I think we can just look at this and see that the only thing that would make my denominator come out to be a 0 would be a 1. Because 1 minus 1 would give me 0. Let's see, is there anything that would make my numerator come out to be a 0? So I know x equals 1 is a possible critical point because that's what makes it undefined. Now let's see if anything will make this fraction 0. The only way to make a fraction come out to be a 0 is if the numerator itself comes out to be 0. And for my numerator to come out to be a 0, let's see, I'll move my 1 to the other side. And I'll divide by negative 2. Which will give me that. And now I could square both sides. So if I were to square both sides, that would give me 1 minus x squared equals a 1/4. And then if I take my 1 over and make it a 1 minus 1, that'll give me a negative 3/4. And right here's where we know we have a problem, because when I square root both sides, I would get an imaginary answer. So what that means is there's nothing that will make my numerator actually come out to be 0. Okay, only imaginary numbers will, and I'm not looking for imaginary extrema, just the real ones we would see on a graph. So the only possible place I might have is at this x equals 1. So it's a matter of, is this an asymptote or is it a hole in the graph? It's hard to tell that when you have square roots in there. So we'll test numbers on both sides to kind of see what happens, and then we may have to check this out and see on a graph if it's actually a hole or if it's an asymptote. So I'll erase this thing since that one didn't work out so well for... Oh, you know what? I just noticed something. I think I missed something back here. When I moved my 1 over, I didn't change my sign. Let's make that big again. All right. So when I move the 1 over, it becomes a negative 1, which changes both of these signs. And then I square both sides. So I have 1 minus x squared in square root equals a positive 1. Square both sides, and I'm going to have 1 minus x squared equals 1. And now, when I move this 1 over, that gives me a 0. And then I square root both sides, and I get x equals 0. Okay, so now I got two possibilities. I have got x equal 1 as a possibility, and x equals 0 as a possibility. All right, so let's check this. I'm so sorry, guys. I messed this up again. I need you guys here to find my mistakes for me. All right, so if I divide by 2, that gives me a 1/2. I forgot to divide by 2 the last time. Square both sides, and you get 1 minus x squared equals a 4th. All right, so now I can take this 1, move it over here and make a minus 1, and I will have negative x squared equals negative 3/4. Change my signs on both sides, square root, and I get x is equal to plus or minus the square root of 3 over 2. Since 4 has a nice square root, I'll go ahead and square it. So I have possible maxes and mins at radical 3 over 2, negative radical 3 over 2, and maybe at 1. All right, so now to make our chart, I took my original derivative when it was written as one fraction, which is right here, and I wrote the numerator and the denominator separately. Here's the numerator, here's the denominator. So I need to know when I plug these numbers in if this comes out positive or negative, if this comes out positive or negative, and then when I divide those two values, will the derivative itself come out positive or negative, so that I know whether I'm dealing with uphill tangent slopes or downhill tangent slopes. So if you take square root 3 and you put it into your over 2 and you put it in your calculator, you'll get 0.87. So the three numbers that are going to divide this graph up are negative 0.87, positive 0.87, and then the number 1. So that's how my chart will get divided up. And so now I need to pick numbers in each of these four regions, plug them into these two, and then divide the two signs to see if the slopes are uphill or downhill. So negative 0.87, a number less than that, would be negative 1. So if I plug negative 1 in here, negative 1 squared is positive 1. 1 minus 1 is 0. Square root of 0 is 0. 0 times 2 is 0. So 1 minus 0 comes out a positive. Okay, and then here, if I plug it in, I actually get a 0. So it doesn't give me a positive or a negative at that mark. So that, looking back on that, when we substituted into our denominator, not only did we got a 1 out of that just by observation, but theoretically negative 1 would have been the case also. So not only does 1 make it undefined, but so does negative 1. That's a plus or minus 1 up there. So that means I need a negative 1 right here on my chart, which means I need one more section. Okay, so now I need to pick a number below negative 1. So if I pick a number below negative 1, that would be negative 2. So if I pick a negative 2 and square it, that's going to give me 4, and that's going to give me a negative square root. So that means the graph doesn't even exist over here on this side. All right, in between these two, we could pick something like negative 0.9. This is take 2 on example 7. Ignore my first attempt at this. I thought it would be better just to start fresh. So we're trying to find the extrema on arc sine of x minus 2 of x. And anytime you want to find extrema, you want to find your derivative, then set your 0 equal to 0, and then also set your derivative so that it can be undefined. So first of all, we got to find our derivative. And if you remember from page 4 in your math Bible, the derivative of an inverse sine, we did it in a previous example, was 1 over the square root of 1 minus x squared. And then, of course, the derivative of a 2 is just a 2. So now we want to figure out what would make this thing come out to be 0, what would make it undefined. So to do that, I'm probably going to add my two fractions together and make one fraction. So to do that, our common denominator would obviously be the square root, because this is like a 2 over 1, of 1 minus x squared. So the first numerator doesn't need anything, but I have to multiply this 2 times this. So 1 minus 2 times the square root of 1 minus x squared. So the only way to make this fraction come out to be 0 is if the numerator itself is 0. So if I set the numerator equal to 0 to see what will make the fraction come out to be a 0, I'll have to solve this. And if I want to know what's going to make the fraction undefined, then that would be anything that makes my denominator 0. So I'll set my denominator equal to 0 also to figure out what makes the fraction undefined, because it's possible to have vertical tangents as well as horizontal. Okay, so to solve this one, I'm going to take this whole term and move it to the other side. So 1 equals positive 2 square root of 1 minus x squared. Then I'm going to divide by 2, and I'll have a half equals the square root of 1 minus x squared. Alright, so now I'm going to need to square both sides to get rid of the square root. So if I square the 1/2, I'll get a 1/4. If I square the square root, they'll cancel each other out, and I'll have a 1 minus x squared. And so now at this point, we could move our 1 over and make it a quarter minus 1. So a quarter minus 1 equals negative x squared. And a quarter minus 1 is negative 3/4 equals negative x squared. I can change these both to positives and then square root both sides. So now when I do that, I end up with x equals the square root of 3 over 2, plus or minus the square root of 3 over 2. Okay, so now to set this one, I set this one, and that's my denominator. That will tell me what makes the fraction undefined. So if I square both sides, I'll get 1 minus x squared equals 0. I can move my x squared over and then square root both sides. So x comes out to be plus or minus 1. So I have 4 possible extrema or critical points. Alright, and so if you think about, we don't really know on this undefined, was that an asymptote on the graph? Or was that a hole in the graph, possibly, for this graph? But when you look back at the original graph is an inverse sine. And we know how to calculate the inverse sine of 1 and negative 1. So these numbers are not asymptotes on the original graph. Okay, so now we need to make our chart using all 4 numbers. Alright, so if we make this chart using all 4 numbers, radical 3 over 2 is the same thing as a 0.87 as a decimal. So I'm going to have a negative 1, a negative 0.87, a positive 0.87 and a positive 1. And I only have 2 things that it needs plugged into, and I'm kind of low on room here. Let me see if I can move this stuff around a little bit. I'll kind of cut it down over to the side here. Alright, so I have to plug this into 1 minus 2 square root 1 minus x squared, and also the denominator of the derivative, square root of 1 minus x squared, and then I divide those two to figure out the overall slope of the derivative. Okay, so if you're picking a number less than -1, you would pick -2. And if you plug -2 in here, I end up with a negative square root. 1 minus 4 gives me -3. So what that tells me is I maybe have undefined, from negative infinity to -1 in this graph, I have undefined slopes. So I can't have multiple vertical slopes. So that probably tells me that to the left of -1, I would say this graph doesn't even exist. We can look at the graph later, but every number over here, you know, -5, -6, they're all going to give me undefineds. And you're not going to have the multiple, infinite number of undefined asymptotes there, so I would say the graph doesn't exist over here. Let's see if the same thing would happen over here. If I pick +2, and I'm going to get the same thing. I'm going to get 1 minus 4, 1 minus 4, so those also become undefined. So probably this graph only exists from -1 to +1. Alright, so if we want to pick a number in between here, it would probably be something like a -0.9. So if I take a 0.9 and I square it, I'm going to get something like a 0.81. And if you take 1 minus that, that will give you a positive value. Right? And so then I take 2 times that, which maybe we should just plug it in the calculator to get an exact value, since we have to do this 1 minus 2. But we know this is going to come out positive, and we just don't know how big it's going to come out to be. So I'll type that in real quick. Alright, so when you plug in a -0.9, you get a 0.13, which is positive. So plugging in here, I get a positive, and let's just do this one over here also, because it should give me the same thing. Let's do a positive 0.9, because plugging in a positive 0.9 is going to give you the same thing as plugging in a negative, so that's also going to come out positive there. On this one, this is going to come out 1 minus 0.81, that's a positive value, and the square root of a positive is a positive, so this one also comes out to be positive, and so does this one. Alright, so now let's check in between these two. In between these two, a good one to pick would be 0. If you plug a 0 in here, you're going to get the square root of 1, and then times 2, and you'll have 1 minus 2, which is a negative. If you plug 0 in here, you'll get the square root of 1, which is a positive. So now, if I have a positive numerator and a positive denominator, that means in between these two numbers, my slopes are positive, which means they're uphill. In between these, I get a negative and a positive, so that's downhill slopes. And then here I've got positive, so that's uphill slopes. So at -0.87, or the radical 3/2, I've got a max, and here I've got a min, which that's what I was looking for, was my extreme values. So I have a max at -radical 3/2, comma something, and a min over here at the positive. Alright, so then we would go back to the original function and plug in our radical 3/2s into my x's. So recall that your original function was a inverse sine. So I'm plugging in positive and then eventually -2. And then I had a minus 2x, I believe. And so instead of an x, I'm supposed to put a radical 3 over 2 there, which means these will cancel out. And so positive value, inverse sine of radical 3 over 2, that means where's my opposite radical 3 and my hypotenuse 2? That would be a 60-degree reference angle in quadrant 1 since it's positive. So 60 degrees means pi over 3. So I end up with a pi over 3 minus radical 3 for my y value. And then if I plug the negative value in, that's going to give me a negative pi over 3, because it'll be in quadrant 4. Since I'm doing an inverse sine, I have to give an answer in the coffee cup handle. So if this is negative, that would be a 60 degree in quadrant 4, which would be negative pi over 3. And then, of course, if I put a negative here, that's just going to make that a plus radical 3. So those are my y values that go right in here. So when I plugged in the negative, I got negative pi over 3 plus radical 3. And when I plugged in to this one, I got pi over 3 minus radical 3. And so there, that is your final answer. Kind of an ugly problem. All right, moving on to example 8. Example 8 is our last example, and we have to find the equation of the tangent line using implicit differentiation. Okay? So, implicit differentiation, doing this with respect to x. I got to know the formula for arctangent, and I believe arctangent was 1 over 1 plus x squared. Remember, instead of an x squared, I'm going to have an x plus y. So derivative would be 1 over x plus y squared. And now, since this is more complicated than just an x, I have to multiply times the derivative of this. And the derivative of this would be 1 plus y prime, using implicit differentiation. All right, and then the derivative of this one over here is going to be a 2y prime, and then the pi over 4 is a constant, so it will become a 0. Okay, so to simplify this, we'll probably first of all all right, so to work this one out and solve it for y prime, the first thing we're going to do, let's write this a little bit nicer. Let's make this 1 plus y prime over 1 plus, and let's actually square the first, square the last, multiply, and double on this thing, is equal to 2y prime. So to get rid of the fraction on this thing, let's multiply both sides times this crazy thing down here. So if I multiply both sides times that, I'm going to have 1 plus x squared plus 2xy plus y squared over here, and this one will cancel when I do that. Okay, so now I've got 1 plus y prime is equal to 2y prime plus 2y prime x squared, just using the distributive property here, for y squared, since I have a y in both spots. I have a y here and here, so I end up with a 4y squared, y prime, and an x. And then for the last term, I get a 2y cubed y prime. Okay, so now I'm going to take this y prime that's here and move it over here so all my y primes are on the same side. And since I have all of these have a y prime in them, I'm going to factor out a y prime. So if I do that, I'm left with a 2y plus a 2yx squared plus a 4y squared x plus 2y cubed minus 1. And so now all I got to do to get this y prime by itself is divide by this long crazy thing here. So, if I shrink this up a little bit, okay, so now I divide, and I get y prime equaling 1 over this crazy thing here. 1 over 2y plus 2yx squared plus 4x squared y actually that's a y squared x plus 2y cubed minus 1. Alright, so there is my y prime, and remember, in order to find the slope of the tangent line, I simply need to plug this point into my derivative, and that will tell me the slope of the tangent line. So if I replace every x with a 1 and every y with a 0, well, this has a y, so that goes away, this has a y, so that goes away, goes away, and all I have left is 1 over negative 1. So that means my slope is negative 1. Alright, so now I know my slope, and I have a point. So if I have a point and a slope, here's my slope, and here's my point. Now I can use point-slope form. So y minus y1 is equal to the slope times x minus x1. And so then if you work that out, you get y equals negative x plus 1. And there you go. That's the equation of the tangent line, and that is all of lesson 5.6.